Welcome to monochemistry. Today we're going to look at the concept of standard enthalpies. Now we've already talked a little bit about this in the sense that we've been dealing with the delta H of vaporization and delta H of condensation, which are opposites to each other, delta H of solidification and delta H of melting. Okay, so those are in the same category as these. But these particular ones that we're going to talk about here, which I'll go over in just a second, are actually for chemical reactions as opposed to physical changes. Those other ones I just talked about are physical, right? For physical processes. These are for chemical processes. Okay, but what does it mean to have a delta H, a standard delta H? Okay, so let's talk about that. So this little symbol here looks like a degree symbol. Anytime you see that, it means standard. And what standard means is that it's at what we call standard laboratory conditions, SLC, standard laboratory conditions. Now, standard laboratory conditions are 25 degrees Celsius and 1 atmosphere of pressure. Okay, so it would be what you would find at sea level in a standard room, 25 degrees Celsius. Okay, so the delta H values for all of these things have been calculated by scientists at those conditions, and that's what the accepted value for each of these things is. Okay, so that's why we have these. We have these values so we have something to compare our results to labs to, so that we can use those values in particular questions. Okay, so these have been tested and tested over and over again to come up with a standard value for each of these things. Okay, so remember, the delta H stands for the change in enthalpy. This means standard. Okay, so standard, change in enthalpy. This little F, that one stands for formation. Okay, we'll talk about that in a second. So the delta H, the standard change in enthalpy of formation, the standard change in enthalpy of combustion. Okay, so a combustion reaction, you have standard delta H's for that. And then there's another one that kind of covers all the other types of reactions that aren't formation or combustion, and it's called the standard delta H of reaction. Okay, and again, all of these things are standardized at 1 atmosphere and 25 degrees Celsius. Let's talk a little bit more about the delta H of formation. Okay, so the standard molar enthalpy of formation, as you can see here, I've got a chart that basically has several chemicals in it, okay? And it shows you what the standard molar enthalpy of formation is. It's called the molar enthalpy because it's in kilojoules per mole, okay? So the definition of the molar enthalpy of formation is this, and you can write this down. The definition of the molar enthalpy of formation is it's the amount of energy to form 1 mole of a substance from its individual elements. It's the amount of energy it takes to form 1 mole of a substance from its elements. Okay? Now, let me just show you an example here. So let's say we wanted to form water, H2O. Okay, H2O is on here. Okay, so let's say we wanted to form water, regular water, liquid water, okay, at room temperature. If I wanted to do that, I would have to, the standard molar enthalpy of formation would involve its individual elements. Well, its individual elements are this: H2 plus O2. Okay? Now here's the thing with this particular reaction. Because I'm looking for the delta H per mole, I can't balance this equation the way I normally would. So instead, what I have to do is I have to make sure I only end up with 1 mole of my product. My hydrogens are balanced, my oxygens aren't. So how do I ensure that I only have 1 mole over here? Well, I have to do something that I told you guys you weren't supposed to do. The only time you will be able to do this is in thermochemistry. Now watch this. If I put a 1/2 here, if I do that, I've now balanced this equation, not the way I showed you, but I've now balanced it so that I can get 1 mole of my water over here. Okay, so 2 hydrogens, technically 1 atom of oxygen will give me, or 1 mole of oxygen, because it's half times 2, it'll give me 1 mole of oxygen, gives me my 1 mole of H2O. Okay? So when you're doing standard enthalpies, it has to be per mole, which means your balanced chemical equation has to give you only 1 mole of that substance. The enthalpy of combustion is a little bit different in the sense that we're looking not at forming a substance, we're looking at burning a substance. Okay, so you guys know a combustion reaction is any type of reaction where oxygen is one of the reactants. Okay, so in this case I'm taking methane, CH4, and I'm burning it in oxygen. Okay, now according to this, over here, this is my little chart, it's in your textbook. Alkane, when combusted, will release 965.1 kilojoules per mole. And then you see all the other ones on here and how much energy they'll release. Okay, so the molar enthalpy of combustion, the definition for that is the amount of energy released when 1 mole of a substance is combusted. Now look at this equation right here. Look, 1 mole of methane plus 2 moles of oxygen yields CO2 plus 2H2O. So you see, and you can write this one down as your example in your notes, okay? Just like the one previously, you can write that one down as your example for the standard molar enthalpies. As you can see, a combustion reaction releases a lot of energy. So what's the importance of that? Okay, what's the importance of that? Well, we use these reactions to provide us with energy all the time. Okay, think about your car. It runs on gasoline, which is mostly octane. Okay, so every time you burn that, that's how much energy you're going to get right there. We burn coal to produce electricity. Okay, so combustion reactions are very, very important to us. We burn oil to heat our houses. Okay, we burn wood to heat our houses, right? They release energy. They're exothermic. So they're very important. It's very important to understand how much energy we're going to get out of that. We can do some calculations around that, especially in the production of electricity. That's key. Okay, so just really quickly, just to sum up here, standard enthalpies, whether it be of formation, of combustion, or of reaction, involve an energy change, right? So delta H, and it's per mole. It's the amount of energy per mole of the reaction. Okay, so if it's formation, you're trying to form 1 mole of that substance. If it's combustion, you're burning 1 mole. And it's of reaction, well, you're looking at one individual thing, whatever that may be, and that's you want to make sure there's 1 mole of that. One quick thing that you should note, in case you haven't already, a positive value for a delta H, standard delta H of anything, means it's endothermic. That means you have to put in more energy than you get out. A negative means you get out more energy than you put in the first place, okay? So just think about the differences between the endo and exothermic. We've talked about those. So that in a nutshell are the different types of standard enthalpies. Don't forget about the standard enthalpies of vaporization and melting, and then the opposites of those. We've already talked about those as physical. The ones we talked about today have to do with chemical reactions. Make sure you take some good notes and bring your questions to class.